Hi, I'm Amir Michael from Group 9 with Joseph Arrigo and Ryan Megan, and our group will be presenting physical and versus virtual memory. In this presentation, we'll be talking about several topics. First, we'll be talking about analyzing programming running stages, where we will be studying and explaining the stages in which a program is run, from the compiler to the assembler to the linker to the loader, and then finally executing. Then we'll be talking about the CPU memory management, such as determining when the CPU produces logical or physical memory addresses, and explaining dynamic relocation in MMUs. Then we'll be talking about segmentation, paging, and page tables, where we'll be presenting the basics of segmentation, paging, page tables, and page replacement policies and algorithms. And finally, we'll be talking about the different architecture variations from x86 to ARM to RISC-V, and we'll be showcasing how they differ from one another in terms of the memory management. So I will be presenting the analyzing programming running stages section. We'll be going through source code, then compilers, then assemblers, linkers, loaders, and then executing. So first, as a general overview, in order for the computer to run the code that the user programs from a high-level language, the computer must first convert the source code into machine code, and then the machine code can finally get loaded into memory for execution by the CPU. There are several steps that this takes. In the beginning, it starts as source code from a high-level language such as Python, or a better example would be Java. And this code will then go into their compiler, which the compiler will generate assembly code. Then this assembly code will be put through the assembler, which will generate the machine code. And then this will then be put into the linker, which will link all the libraries used in this code. And then this will be put into the loader, which loads into the program memory, or loaded into the memory and can be ran and executed. So, as an overview for compilers, once the user writes code in the preferred language and wants to run the code, it must go through the compiler first. The compiler's job is to translate the high-level language code into assembly code, and it does this by first reading the source code and performing some checks, such as making sure that the program follows the lexical, semantic, and syntax rules of the programming language. And then after the compiler performs these passes through the code, it then optimizes the code and generates the assembly code based off these optimizations. And we'll be discussing the more in-depth explanation of these steps later on. But on my right, you can see these steps in action and in order. Well, you start with lexical analyzing, and then syntax and semantic. And then through this, you can get the intermediate code generator. And then this will get put through the code optimizer. And then you can get finally the assembly code that you want in the end. So some of these steps we'll go into more depth. First, the lexical analyzer. So the compiler reads the source code and converts it into tokens, which tokens are basically the smallest unit of meaning, such as keywords, identifiers, operations, and punctuations, such as multiplication and addition. And then the syntax analyzer. In the syntax analyzer, the compiler checks for code syntax errors and makes sure that the source code follows the programming language's rules. An abstract syntax tree, or AST, is generated, and this represents the code structure as shown to the left with the AST and the parse tree. Then the semantic analyzer checks to make sure that the code has a proper meaning, no logical errors, such as assigning variables before it is declared or assigning the wrong type to a variable. And then last, after all of this, the code generation pass is performed where the AST is translated into assembly code. And just as a review, compilers allow developers to write code in high-level languages which are more human-readable and easier to understand. They will also allow for cross-compatibility where software developed on one platform and architecture can be used on a different platform and architecture. So there are many different types of compilers that each serve their own purpose. For example, native code compilers will only compile code for one platform. Cross compilers will compile code that can be run on multiple platforms or architectures. One pass compilers are basically compilers that compile in only one pass, where in that one pass each line is tokenized and then evaluated for correctness and then translated to assembly language. And then there's multi-pass compilers, which scan the whole source code, makes a modified structure, and then uses a modified structure for another pass. And examples for the most common used compilers is GCC and Clang for C. And for Java, there's the Eclipse IDE, which comes with an built-in Java compiler. So for code generation, one type of compiler that depends on recursive descent parsing, where a string of commands from an input language is the input into the compiler, and the assembly language is the output. And this works by before writing the compiler, the input language is analyzed for patterns and conditions. The compiler then passes the input to functions that call one another to analyze the characters being input, and from these functions, the output assembly code is generated and built procedurally. So now that the code is converted into assembly code, we are able to convert the assembly code into machine code. And this machine code is specific to each platform OS, and it's binary data, ones and zeros, that can be directly executed by the processor. The assembler also resolves symbolic names and addresses to their values and generates relocation information for the next phase, which is a linker. And the assembler has two phases. The first one being the analysis, where it breaks down the assembly code into smaller building blocks such as symbols, labels, and instructions. It then validates the syntax of the code, checks for errors, and creates a symbol tree that maps the symbols to memory addresses. And then the next step is the synthesis phase, where the assembler will then convert the assembly language into machine code using the symbol trees memory addresses for each instruction. Next is the linker, and the linker merges all machine code modules like libraries and object files into one single executable file. It resolves memory references and symbol references and relocates relative addresses to absolute addresses. And there are two types of linkers. A static linker, which is performed during the compilation of the program. It takes a collection of object files and generates a fully linked object file. And this method has two primary tasks: symbol resolution and relocation. And then there's dynamic linking, which is performed during runtime, where the name of the shareable library is placed in the name of the execution table, and the shared library is needed in linking is stored in virtual memory. And even though there's higher chance of errors or failures, it requires less space as multiple programs can share one single copy of the library. And as a summary, linkers allow for greater code modularity and reusability by breaking a larger software program into smaller objects that can be linked together, developers are able to create more modular and reusable code. Last, we have the loader and the execution stages, where the loader allocates memory from the program segments and data and loads the final resulting executable code into this memory from the disk. It also sets up the program stack and registers and then transfers control to the CPU. And lastly, the execute stage is the stage where the actual original high-level code is executed via the produced machine code output. The CPU executes the code instructions one by one following the program logic. And the next segment is CPU memory management, which will be discussed by Joseph Arrigo.
Hi, I'm Joseph Arrigo, and over these next few slides I'll speak briefly about how the processor manages and interacts with memory on a physical level. So the first aspect of a CPU's memory management system that we're going to talk about is the addresses. There's two types of them in a CPU, virtual and physical. A virtual address is used by the CPU to refer to a physical address where the data literally is physically stored. This separation of the CPU's programs and physical memory stops programs from directly modifying physical memory. So instead, the programs are forced to go through whatever virtual addresses are created and managed by the CPU and OS. This lets them manage memory for efficiency or prevent errors from occurring. This barrier between virtual and physical is possible because of the Memory Management Unit, or MMU. The MMU is a physical component that translates incoming virtual addresses to physical addresses. Once those physical addresses are generated, the hardware can do whatever memory operations it needs to without the CPU or OS having to know the actual physical address. Now, when it comes to running a program or any set of instructions really, there's two primary ways of managing memory, dynamically and statically. Having a statically allocated program means that it has exactly some value of memory allocated to it, never any more and never any less. The other way of managing memory is using dynamic relocation. If you've ever written a line of malloc for C code, you've dynamically allocated memory. Basically, dynamic relocation is when allocated memory is determined by the program being allocated or reallocated. But one big drawback that emerges from it is the need for cleaning up any used memory when a program is complete. Any dynamically allocated variables will not be automatically cleaned up after execution, and they must be freed in the code. This is because at a machine level, dynamic relocation works by using the MMU to change the physical address corresponding to a particular logical address when the memory is referenced. Two more of the hardware registers on the MMU beyond just the relocation register are the base and bound registers. The base register is what is actually pointed to by virtual address 0, and the bound register represents the maximum virtual memory address value. Every time memory is referenced, the virtual address is compared to the bound register and it's added to the base register to translate it into the physical memory address. If it's beyond the bound, a trap is made to the OS to handle the exception. The advantages of this method of memory management are that it's simple, inexpensive, there's data safety and security built in, and dynamic relocation is possible. But the disadvantages are that each process must be actively stored and referenced in physical memory, and no memory can be shared.
Hello, I'm Ryan. I'm going to be presenting section 3 where we'll be covering segmentation, paging, page tables, the process of how the CPU accesses DRAM memory, and thrashing. So first is segmentation. Segmentation is where a process's address space gets divided into segments. Each segment can have their own size and protection attributes, can grow and shrink independently, and can be loaded and unloaded independently. The top bits of the segment correspond to the logical address of the segment, and the lower bits will correspond to the offset within the segment. The MMU will contain a segment table for each process, where each segment will have its own base, bounds, limit, and protection bits. And we can see this a bit in the top left and right image, which shows a more technical look about how this process works. The main advantage of segmentation is it has good CPU utilization, segments can be shared, and the space can be allocated sparsely. However, the main disadvantage of segmentation is that it generally takes more time to retrieve instructions, and the segments have to be allocated continuously. This may cause external fragmentation, which is where, although we have enough memory in total for a new process, we do not have a continuous block of the required size. So you can see this in the image where if we're trying to allocate 63,000 bytes for a process, but we do not have a free block for this size even though the total memory is more than 63,000 bytes. And we can fix this using a process like compaction. Paging is a form of dynamic relocation where we divide physical memory into frames and the logical address space into pages. Pages will always have the same length as the frames, where the size will be any power of 2. This is just because it makes it easier to translate a virtual address into a physical address. The most common page size is between 512 and 8,192 bytes for a system, although 4,096 is the average. So pages are important because they help to solve the 90-10 rule, which is where a process spends 90% of their time accessing only 10% of their memory. So paging will help us keep only important parts of a process in memory that we need to use. So pages can be swapped, shared, and they do not need to be allocated continuously. So this helps eliminate the external allocation that we discussed earlier. And just in case if you don't know what swapping is, it's when a process is moved from main memory, like the RAM, to a secondary storage device like a hard drive or solid state drives. And computers do this just to offload inactive processes from main memory so that the active processes have more available memory. Page tables are an abstraction layer that stores the mapping between a process's pages and physical frames. It is used by the MMU for translation, where we have to do table lookup and bit substitution. You can see this in the image to the right. Allocation in a page table is easy. We basically just keep a free list of available pages, and the system will just grab the first one. And because all pages are the same size, it is very easy to perform a swap. Since page tables can be large, systems use the multi-page tables and TLBs. TLBs store a hardware cache of recent translation in the form of a key value pair, where the key is the page number of the virtual address and the value is its corresponding frame. And to create pages, we follow this general process. We're going to allocate K page frames, freeing the old ones if they're not needed to make more space. The pages are going to be put in the frame, and the frame will be put in the page table. The OS is going to flush out the TB, and the process will be started. And as the process executes, the TLB entries are loaded as pages are accessed, and entries get replaced if the TLB comes full. TLBs are typically 8 to 2048 entries in size, and for each memory reference, the page number from the virtual address will be compared to the page numbers in the TLB in parallel. And if a match is found, the page number in the TLB will be used. Otherwise, we will have to go through the translation process and replace an existing entry in the TLB. TLBs overall drastically reduce the average memory cost due to reducing the amount of translations that need to be performed. The only downside of the TLB is that if a process moves, its virtual mapping changes and we must invalidate some TLB entries. And if we switch from one process to another, then we have to invalidate all the entries. And we can tell this when the page table register changes. So there are multiple ways to access virtual addresses, such as with the base and limit registers, paging, and segmentation. Paging is most often used, which we explained earlier. And there's another method called page segmentation, which pretty much just combines the benefits of both paging and segmentation at the cost of more complexity and processing speed. Page replacement policies refer to how a page should get removed from memory when a page fault occurs and a new page needs to be loaded. A page fault occurs when a process attempts to access a page that is mapped in the virtual memory space but is not loaded in physical memory. The general goal of the page replacement policies are to minimize the number of page faults that occur by keeping the most frequently used or most recently used pages in memory. Some page replacement policies include first in, first out, or FIFO, least recently used, or LRU, which is most widely used in operating systems, least frequently used, or LFU, and optimal, or OPT. FIFO replaces the page that has been in memory for the longest, and it does not perform too well just because it does not consider the frequency or recency of page usage. LRU replaces the least recently used page in memory and performs better than FIFO, but is more complex and costly to implement. LFU replaces the page that was accessed the least, performs better than FIFO, as it considers the frequency of page usage, but it might result in aging. And this is where a page that was frequently used in the past but was not recently used will remain in memory, preventing more important pages from being loaded. OPT replaces the page that will be used farthest in the future. It is the best method, but is not theoretically possible just because it requires prediction of future events. So for thrashing, every process needs a minimum amount of pages to execute, and if it is unable to get the minimum amount it requires, a page fault will occur. When this happens, pages will have to be replaced, but in the situation where all pages are in active use, a page needed in the immediate future will be replaced, and this cycle will keep occurring until an active process terminates. This high paging activity is called thrashing, and will occur whenever there are too many processes competing for a limited amount of memory. System performance as a result will be heavily degraded. So this will generally occur because of insufficient memory to handle the processes that the user wants. The page replacement policy does not reflect the actual usage patterns, like FIFO as we mentioned earlier, and there is high CPU utilization, which is where processes are running faster and are using more pages than normal. To fix thrashing, there are 3 potential solutions, 1 hardware and 2 software-based. The hardware-based one is increasing the physical memory of your computer. The software-based ones are using a better replacement policy, like LRU, and implementing software that helps control the utilization of processes better. Alright, and with that, Joe will present the final section now.
Hi, it's Joe again, and now I'm going to be covering some different variations of memory management systems across different architecture types. When it comes to ARM processors, translation look-aside buffers don't have an exact structure. Because ARM is a CPU architecture for which there are multiple varieties, each variety can differ in accordance with its own needs. But there are some general trends that are typically followed. First, there's generally one or more micro TLBs located physically close to the instruction and data caches. Next, the MMU in ARM processors typically uses a table walk unit to quickly read the translation tables stored in memory and translate virtual addresses to physical ones. And finally, the TLBs inside of ARM processors have configurable replacement policies by using signals. ARM is also capable of working with multi-level page tables, but the size of the pages is not determined by the processor. Instead, that task is left to the operating system. In terms of ARM's approach to memory management, it's very standard when compared to other types of CPU and memory architecture. The MMU in ARM systems allows separate programs to be able to use the same virtual address space. And, unlike several other architectures actually, ARM architecture allows the MMU to be enabled and disabled. For some operating systems using the thread model instead of the process model for running software, the MMU isn't completely necessary, and disabling it could lead to faster memory load times. However, this disabling of the MMU comes at the cost of worse data security, and if a virtual address cannot be translated by the ARM MMU, an abort exception is generated on the processor. The next architecture we'll be discussing is x86-64, also sometimes referred to as Intel 64 or even AMD 64 architecture. Now, the Intel 64 architecture uses a 4-level page table. This is double what ARM uses, and as it was mentioned before, this high amount of pages comes with an increased overhead cost, and it's somewhat more inefficient when a miss does happen. The only advantage from it is that misses are less likely. The Intel 64 architecture actually does support multiple page sizes, but its support is extremely limited and it's based on a configuration setting and nothing else. There are only 2 possible configurations for it, regular and extended. Using regular paging grants the processor a fixed page size of 4 kilobytes, and virtual addresses are segmented to have 4 indices. However, extended paging reduces the amount of pages used to 1 only, and the page size is set to 4 megabytes. The main motivation for using extended paging is to allow support for virtualization of physical memory. Now, unlike with ARM processors, the MMU can't actually be properly disabled in an Intel 64 processor, and when that MMU fails to translate a virtual address into a physical one, a page fault is signaled to the OS to be handled. And interestingly enough, Intel 64, or x86-64, is based on a simpler 32-bit architecture called x86, or also IA32. I should also mention at this point that Intel 64 is technically able to support a 5-layer page system. However, it's more inefficient than 4 pages, and the virtual addresses would be segmented even more. The final architecture I'm going to be talking about is RISC-V, although truth be told, RISC-V isn't an explicit architecture. Instead, it's a standard for architecture that supports the reduced instruction set. As such, it allows for several different memory management techniques and practices. So, we're just going to talk about the SV39 translation system. SV39 allows for up to 3 levels of page tables. This actually provides a nice intermediary amount of page tables. It lies between ARM and Intel 64, so one can argue it has the best of both worlds. Having fewer page tables than Intel 64 allows it to avoid some of that larger overhead that comes with 4 levels, but having more than ARM lowers the likelihood of page faults/misses occurring. Now, unlike ARM, Intel 64, and IA32, RISC-V requires a 4 kilobyte page size regardless of which translation method is used. This deviates from the norms established by ARM and Intel, because ARM allows the OS to determine page size and Intel has multiple configuration options for page size. However, one might argue that the standardization of page size can make programs more compatible and more easily adapted between different processor architectures. Another comparison between RISC-V and the other architectures we've discussed is that it's impossible to disable the MMU for RISC-V. Again, this goes for not only the SV39 system, but all the others as well. And this is in opposition to ARM's ability to disable the MMU, but it's similar to Intel's inability to do it. And all this seems to suggest that ARM's ability to disable the MMU is unique for processors. Now, with all of that being said, this is the end of our presentation. We'd all like to thank you for viewing it, and if you have any questions at all, please reach out to us. We'd be happy to answer them.